Thank you so much. And thank you so much for dealing with all of the times that I had to change my talk schedule around when the Sgr announcement kept getting moved. So I really do appreciate that. So as Sia just said, I never gave one of these before because I kept thinking that, oh, I'll just wait one more semester and then I can talk about Sgr. And that one more semester became 3 years. So with that in mind, finally able to actually tell everybody what it is that I've been doing for the last 3 years that I've been here. And so I know that we had a wonderful talk last week by George. George and I chatted. I specifically removed everything from my talk that was clearly overlapping with what he talked about so that hopefully you guys won't be too bored. But that does mean that I'm leaving out a little bit of the introductory material. So if anything is unclear, please do stop me and let me know. I'm going to be specifically talking about paper 6 today, because that's been my life for like the last year and a half. So we had 6 collaboration papers. They each had 2 to 3 coordinators, and I was one of the coordinators for paper 6. And so after a year and a half of work on that, I want to talk about it. Before I move on from my title slide, I'm not just trying to hypnotize you guys with my purple swirly, although I do really enjoy my purple swirly. The reason I like to show this, so this is a Sgr A HD general relativistic magnetohydrodynamic simulation that we then did ray tracing and radiative transfer on top of. But the reason that I like to show it is that I think it illustrates a couple of the basic principles that will really be important for the whole talk. So this is actually a free color image. Blue is 1.3 millimeter wavelength emission, and that's the wavelength that the EHT actually observes at. Green is 0.8 millimeter emission. I know it's a little hard to see green. That's because I don't like green and I messed up the color ranges. But I promise you that there is green here. 0.8 millimeter emission is the wavelength that the EHT will observe at soon. And red is 3 millimeter wavelength. And the reason that this is interesting is because you can see that there's this very thin white ring here that is A, achromatic, and B, completely constant while everything else varies around it. That's right at the boundary of the black hole shadow, and that's going to be the main thing that I'm going to be talking about today. Oh no, I checked this earlier and it worked. Okay, well, we'll figure this out. So before I give any of these testing gravity talks, I always like to be really clear about what it is that we're actually testing, and that's a really important part of this entire talk, essentially. So in paper 6, we included this plot where we tried to place different tests of gravity within this parameter space, I guess, but it's not really a parameter space. But the point that I want to make here is that when we're talking about testing gravity with the EHT, what we really have is a huge supermassive black hole with a really tiny amount of matter that's swirling around it. And so in everything we do, we ignore the effect of that matter on the space-time. And we're essentially treating it as a stationary black hole in vacuum. And so you can do whatever you want to the dynamics of the theory and it won't affect anything that we do really. And this is in contrast to, for example, black hole mergers with gravitational waves where you're sensitive to both the dynamics and the metric. And so just keep that in mind that we're really just doing a metric test and that's all we can really ever hope to do. Now it's working good. So as promised, I will define what the black hole shadow is. This is something that has existed in the literature for quite some time. We did do a very extensive literature review, looked at probably 300 or so papers, and the definition that we ended up going with is the one that is the most common in these 300 papers that we've looked at, and that's essentially the critical impact parameter. And so what I mean by that is in this diagram, the shaded disk here, this is the event horizon, green circle is the photon orbit. I'm going to send a bunch of photons towards this black hole. All of the blue ones will fall into the black hole. All of the red ones will escape to infinity. And we define the black hole shadow boundary as the boundary between these blue photons and red photons. So we're actually going to zoom in a little bit here. And we're going to look at what happens to the photon that's right at that boundary. And you'll see that that photon is essentially tangent to the photon orbit. So this critical impact parameter, I think, is the simplest definition, but you can also think about this as the lensed photon orbit. Mathematically, you get the same result. The size is square root of 27 GM over C squared, and is about 2.5 times larger than the event horizon. And so I do want to also advertise that I this beautiful animation was made by my student. He's doing his master's with me, and this was using a new radiative transfer and ray tracing code that he is developing as his master's thesis. So he will be on the graduate student market. People need grad students next year. So the diagram that I just showed you was for a Schwarzschild black hole, but of course we do expect that black holes in space will have spin. So the next obvious question to ask ourselves is how does spin affect the size and the shape of the black hole shadow? So this blue circle here, this is the black hole shadow boundary for Schwarzschild. But when I play the animation, the spin axis will be pointing up and you will all be observers at the equator. And so I'm going to go ahead and play this, and you can see that the shadow moves over to the right. But at least so far, the size and the shape really hasn't changed that much. And it's only when we get to really high spins that you can see this deviation from circularity there. And obviously to our eye, it is a very clear deviation from circularity. But if you were to measure the asymmetry of this shape, it's actually still really low. And in particular, this is not something that we can really constrain with the current EHT. This size of deviation from circularity is just too small for us. And so there are a couple ways that you can look at this. You can be a little pessimistic and say that this is really horrible because it means that it's going to be really hard for us to use the size and the shape of the black hole shadow to constrain the spin of the black hole. Or you could be a little bit more optimistic about it and say that this is actually really great because it means that we don't need to worry about free parameters and we can just test whether or not this black hole is consistent with the curve prediction without really having to worry about the effects of spin. And so if we ignore the circularity, but if we just look at the size, for all inclinations and all black hole spins, the range of sizes for this black hole shadow is between about 4.8 and 5.2 GM over C squared. It's about plus or minus 4%. So it's actually really small compared to the error bounds that we have with the EHT right now. Okay, so I've defined the black hole shadow in a way that depends only on the metric of the black hole, not on any astrophysical effects. But of course, what we actually observe does have astrophysical effects. So the next question to ask ourselves is how does this geometrically defined feature relate to a possible observational feature? And so I've included 3 bullet points here. These bullet points originally came from paper 6, 2019 M87 EHT publications, but we've essentially paraphrased this in paper 6 for Sgr because I liked it and I included it. So these 3 bullet points are essentially the necessary conditions, and we argue that if these conditions are met, then this observational ring feature will be related to, within a particular error bar that I'll get to, will be related to this black hole shadow feature. So first, we need enough photons to actually illuminate the black hole. Second, the emission needs to originate close enough to the black hole, but primarily outside of the photon orbit so that it will be gravitationally lensed around the black hole. And finally, the surrounding plasma has to be sufficiently transparent at the wavelength that we observe at. One thing that I really want to emphasize here is that we didn't just get lucky. This isn't like a super fine-tuned thing that we just happened to get super lucky that this worked out. This was by construction. We knew these things and we had accretion models, we had simulations, and this is why we chose this wavelength. This is the wavelength at which these things are true for both M87 and Sgr. So this is by construction, not by luck. So this simulation that you see over there, this is what you would see if you were looking at a black hole at 1 centimeter wavelength. And so you can see this big poofy disk. That is important to keep in mind that for both M87 and Sgr, they're low luminosity accretion flow. So we do expect the disk to be very poofy, not thin. And so at 1 centimeter, you can see the poofy disk, you can see these jet features, but you can't see the shadow. And so I'm going to go from 1 centimeter all the way down to 1.3 millimeters, and you'll see how the effect of changing the wavelength changes the optical depth of the disk, and we'll be able to see all the way through the disk down to the shadow itself. I think this is one of the most fun animations that we have. So CK Chan actually made this. I just think it's beautiful. So anyway, so at the bottom here, I've included a different simulation. And the point here is that I've also included in the middle and rightmost panels, vertical and horizontal cross sections of the image on the left. And these dotted, or I guess dashed vertical curves here, lines, are the analytically calculated black hole shadow boundary. So I'm going to play this. There's going to be a lot of variability, but what I want you to focus on is 2 things. One is that, yes, there is this thin peak here that's right at the shadow boundary. None of our results depend on actually observing that. It is bright, yes, but it's very thin. And so the actual total flux that we get is not that high from this little peak here. Second thing I want you to keep in mind is that there is a broader peak, and that broader peak will have significant variability, but it's actually really hard to create a situation where the black hole shadow boundary is completely disjoint from this broader peak. So I'll let that play. And the other part that I think I've already kind of alluded to in my title slide is that even if you can create a ring that is disjoint from the shadow for an instant in time, it's even harder to make that ring that's disjoint from the shadow be constant as a function of time. And so that is a significant part of our argument, is the fact that for both Sgr A and M87, the ring features that we see do seem to be pretty consistent as a function of time, which gives us a little bit more confidence that what we're seeing is actually gravitational or a lensing feature. Okay, so why is it? Yes, please.
So I actually did not know that the existence of jets in Sagittarius A star was very well established. Like this,
Oh, I'm not arguing that it
news
is.
to me, but you said that at longer wavelengths we see that feature observationally or not?
Sorry, I should have clarified. That's not what I meant at all. I'm not in any way claiming that we have observed a Sag A star jet. All I was trying to say was that in that particular animation, that particular simulation, which is just one example, I'm not saying it's the world's greatest example for Sag A, but in that particular feature, out 1 centimeter, you could see these features. The point there was just the optical depth point, but not, I was not trying to make any statement about the jet.
But observationally, is there any evidence, like not even necessarily from EHT? I mean, I know about the that there's something in either WMAP or Fermi or both, but that's on much in a completely different scale. So what about in the nucleus? Like, is there any evidence for an elongated feature?
As far as I know, no. The way that I operate is that there's hints, and I've watched talks where people like argue for this, but as far as I'm concerned, there is no conclusive evidence that there is anything like this. But there are people looking for it, and it is something that people are interested in. But at least for me, I don't believe it. But I'll be very excited if we do find it. Yeah. Okay, so I want to go into a little bit more detail here why we expect to see this broader thicker ring, and why we think that the black hole shadow should be contained inside of that. So in this animation, horizon is in red, photon orbit is in blue, and there's a photon trajectory right here. Your observer in this case is at the bottom of the screen at infinity, and we're going to change the impact parameter that we're sending this photon, and it's actually not just one photon, it's actually a packet of photons. We're going to see how the lensing of this packet of photons is affected by this different impact parameter. I'm going to let it play a couple of times, then I'll highlight a couple different regimes and what's really going on here. Okay, so what you should be thinking about is really the second bullet point from my previous slide, where I've argued that the emission will originate from close to the black hole, but still primarily outside of the photon orbit. And so specifically here, what you should be thinking about is that if you look at these red photons, the red photons will pass through this region here. They will pick up some emission. So on the observer's image plane at that impact parameter, which is inside of the shadow, we do expect to see some emission. And it's essentially emission from stuff between us and the black hole. For the green photons, they will pass through this region over here. And so we do expect to see some emission on the image plane outside of the black hole shadow as well. The black photons are right at the black hole shadow boundary. And so they get lensed really significantly, and they probe almost all of the region where you expect to see the most emission. Now, there is a lot of simplifications in this diagram, and let me make sure that I'm clear about that. We're completely ignoring the fact that the matter is moving relativistically, probably, right? And so there's that relativistic Doppler beaming and boosting that definitely affect this. We also have to take into account the redshifting effect. We have to take into account the inclination between us and the disk, optical depth, emissivity, all of those things obviously need to be taken into account, and they are taken into account in the actual simulations. This is just a very simple toy model to hopefully build a little bit of intuition.
And where the observer is in this?
At the bottom of your screen at infinity. Yeah, sorry. So I think now it's going to build again. Sorry. Okay, good. So in addition to these arguments, we also did test this, right? And so as part of the gravitational physics working group in the EHT that I've been leading for the last 2 years, there have been several papers that have come out that are trying to test this, this relationship between the observational feature and this geometric feature. And so this is just 2 of them, and I'm just going to focus on these because these are the ones that we ended up using for paper 6. And so what these plots are showing you are the results of comparing the size of the analytic feature to the size of the ring feature in an image. And so I want to be very clear here. We're not actually doing a synthetic observation. So we're just comparing the ring in this perfect simulated image when we apply essentially a feature extraction algorithm to that perfect image to this analytically defined black hole shadow feature. And so the x-axis in each of these is showing you the fractional diameter difference between these 2 features. And in all of them, the y-axis is showing you the full width half max along the ring over the shadow diameter. And so it's showing you the distribution of these. And my argument throughout has been that it's hard to make this joint rings. And the red shaded region in each of these plots, this kind of triangle shape here, the red shaded region is where you would be if you were disjoint. And so the top 2 panels are for GRMHD simulations. One of them is prograde rotation, one of them is retrograde rotation, and the bottom 2 are for non-Kerr metrics. And so the one on the left is for a metric that is a parametrized metric. So the idea here is that you deviate from Kerr parametrically. You have a bunch of free parameters you can vary. And the other one is an EMDA metric. And for the purposes of this talk, you just need to know that it's a specific solution to different field equations. And so what they're doing here is that they're using a analytic accretion model that relaxes some of the assumptions that go into GRMHD, trying to vary that as much as they can, trying to break this relationship. And it is actually really hard to break it. I will say that there are some images that do break it for the JP metric, but that's at like the 95th percentile. And we did look into why that was, and there is a discussion about it that I won't get into now, but it's actually pretty hard to make that happen. And so for paper 6, we used essentially the same set of simulations that I just showed you from those other papers, but we also added to it significantly. And so this is a histogram of the fractional diameter difference between these 2 features. And we had essentially free data sets that we used to make this calibration. So the first is shown in blue, and that's from the GRMHD Kerr models. And so we have hundreds of thousands of images that were used in this analysis. And yes, please, go ahead.
Finish your thought.
Oh, I was just going to say that we don't only use the ones that are consistent with Sgr. Like we don't down select our GRMHD simulations and only use the ones that are actually like the preferred models, but we use all of them. George, go ahead.
So if you go back to the previous slide, so for those models that are inconsistent, would you be able to notice this observationally if you allowed the mass to change? So for, I mean, what is this? I guess I'm asking, so for example, if we don't look at the non-GR stuff, and I'm thinking in terms of M87.
So you're looking at these 2.
No. So
you're looking at this
about that one, but I'm framing this in terms of a question.
Okay.
So I'm thinking in terms of the M87 results from however long ago. We were able to rule out the R high equals 1 stuff because it just looked very different. So I'm wondering if in the models where there's a large deviation where you don't have, so does it just look so different that you could rule it out for different reasons?
Honestly, that's a really good question. And I mean, from my perspective, we were explicit in not doing that. Like we do not have any other cuts on this data set in any way because we didn't want to have any bias. I think that, yeah, probably. But I also think that like, these are pretty extreme situations to like, you had to push things really perfectly, right? It's at the 95th percentile. And even then it's like just barely into this region. But yeah, I think what you're saying, probably. But we really try not to do that. Yeah. Any other questions? Yeah, go ahead.
More like a general question. Do you need to use full GRMHD simulations for these modified metrics, or is this just an analytical correction?
These
come together.
Good question. This entire slide is not GRMHD. Yeah, so there is the GRMHD that is on the next slide, and that is compared to these results. And so we do GRMHD with all of the GRMHD assumptions, but also has variability and turbulence and all of that, right? So it can create reasonable broad range of image morphologies. But then we have these analytic models where you can loosen some of the assumptions that go into GRMHD, and you can probe as wide of a parameter space as you want to with these models, but then you don't have the turbulence, the variability, that aspect of it. Yeah. And so a little bit divide and conquer. Sorry, yeah.
You don't have to cross-check that? Do you have?
What we ended up doing was we did the entire analysis, the full calibration with this, and also the full calibration with the GRMHD, and found very similar results. But we were trying to check, right? We're trying to check whether these assumptions that go into GRMHD make a huge difference, or whether this would be way too limited, or things like that. Yeah. But part of the reason for this, by the way, is that it's tricky from a numerical point of view to run a full GRMHD simulation in a non-Kerr metric. Like, that's not a trivial thing to do. And so this is a way to include a wide range of non-Kerr metrics in a more realistically feasible way that would not take 3 more years of our time.
Is there any, is there any conceptual challenge to running this, or is it just that the metric makes the post-processing more difficult, or
I mean,
or is it difficult?
So for example, for JP, right, there is no self-consistent theory that predicts these parametrized metrics. You're just treating it as geometry and ignoring the rest of physics. Exactly. Right. And so then you'd be assuming that everything else in physics and everything else about GR stays exactly the same, but magically the metric just changes. Sure, okay. I mean, for what it's worth, JP is the metric that has the least pathologies, but most of these you will end up running into pathologies. And once you have like a closed time-like loop in a GRMHD simulation, you have a problem. But there are people in this working group. This is something that we're actively pursuing, and there was an effort to include actual GRMHD simulations in this. It was just a matter of like people power and how hard I could push my team to keep going, and I tried, and people were busy, and that didn't get done in time. Yeah, but it is something that we are actively pursuing. Yeah. Any other questions? Okay. So as I was saying, this is from paper 6, and so we use all the simulations that you just saw, and then we added many more simulations. So blue is for the GRMHD, orange is analytic models, which is what you're just seeing for Kerr, and there are hundreds of thousands of images included in that. And then the analytic non-Kerr is shown in green, and there's again hundreds of thousands of images included in that as well, and those are essentially a subset of them were shown in the 2 plots at the bottom of the previous slide. And so the first thing is that you don't see a drastic difference between the distribution of these histograms for Kerr, non-Kerr, and analytic versus GRMHD, which I think is really reassuring personally. And the other thing I do want to talk about is I want to talk about a little bit more detail how we actually are going about this calibration. So we define the measured ring diameter in the EHT images as dm, and we define the shadow diameter for short child, not Kerr, but for short child, as the shadow. And alpha C is the total calibration, and we divide alpha C into 2 sub-alphas, so alpha 1 and alpha 2. There are reasons why we did this. This did make things a lot clearer and a lot more, we were able to do a much more comprehensive calibration by doing that. So alpha 1 is the difference between the analytic feature and the feature in this perfect image, and alpha 2 is the difference between observed image and perfect image. So obviously everybody's seen this by now, but this is the image that we published, one of them. There are actually hundreds of thousands of them. I just want to point out the parts that I think you should trust and the parts that we need for the things I'm going to be talking about today. So there is a brightness depression. That is important. We do use that. I do believe that. I do think that it's okay for you to believe that. Second, there is a ring. I don't think that you should worry about the fact that it doesn't seem super circular, because we do not believe that. Everything we're doing is totally consistent with a perfectly circular ring. We can't really tell right now, at least. But there is a ring, and we can measure the size. And as again, one of the things I'm super excited about for future EHT is being able to get the shape down, but this really isn't something that we have a good handle on right now, given the quality, not the quality, but given the amount of telescopes that we had, the baseline coverage that we had. There are these 3 bright spots. Do not believe those. Do not waste any time thinking about what those are. Those are probably artifacts. If you give us a perfect ring and we do a simulated observation of that, we will create spots. So don't, obviously there are so many different theoretical ways that you could create these spots. Like they're not a problem, right? Like theoretically, we could totally create a model that's consistent with that. You just really shouldn't worry about them because they could totally be artifacts. Okay, so for paper 6, we used hundreds of thousands of images. I'm assuming George talked about the clustering, so I'm not going to go into details about that. The only thing I do want to say is that there were hundreds of thousands of images. We did do this clustering. There are 4 clusters. One of them is the smallest cluster, not very ring-like. The point here is that we use all 4 clusters, all of the images, and everything we do in paper 6. We don't down subtract, like we don't down select. And so even though these things just look like free blobs, you can actually still measure a size of that because you can assume that those blobs are around the ring and it's all perfectly consistent with everything we're doing. So we're not down selecting. And so these are the actual results that we get from the 3 different imaging pipelines. And so I'm not going to go into the details of the algorithms, but the point here is that we treat them all as equal but separate. So we do the full analysis for one self-consistently, and then we do the same thing for the other self-consistently as well. And so there are some significant differences that you can see between the different algorithms, but they all broadly consistent with a ring that has a diameter of about 50 microarc seconds. And so we also do Fourier domain modeling. So the idea here is that why do you need an image, right? Can't you extract the information that you need from the data without having to actually create an image? And so here you're just trying to fit geometric shape to the data and trying to extract the basic things that we want to know, which are the size and width of the ring, the depth of the flux depression, and whether there's any asymmetry in brightness along the ring. And so these are examples of actual fits to the data. And this is the posterior that we get from the MCMC from that fit. And so it is significantly different from the 50 microarc seconds that we get in the imaging. We do think that this is a systematic error, and that is part of our calibration. And we do treat this again. We do the full thing for these geometric models, but we do treat them separately. And so this systematic error is taken into account. And so
why do you think the systematic error is in the Fourier domain and not in the image domain?
Yeah, so that's like an entire talk. Yeah, that's been so much of my last year. So fundamentally, when we try to fit for a simple geometric shape to the data, you're inherently going to have some biases that can come out because we know that this is an overly simplified model. Like we know that it's not going to necessarily be enough to contain all of the information or really match the image morphology that we have. So there's a paper that I was very involved in that came out in 2020 that looked in a lot of detail at the biases that you get when you just use a simple crescent model for this. And one of the things that we found is that there's like 3 or 4 data points that are right at the location of the first minimum. If you remember the M87 data, it looks kind of like this. It's a Bessel function essentially. The 3 or 4 data points that are right at that minimum have like way more power and way more control over the overall fit than all the other ones, right? And so it's super sensitive to that. And on top of that, what we know is that there is a pretty well understood, and this is something that was in the 2019 papers already, a known correlation between the width and the size of the ring, where you can make different images where you change the width and you change the size in such a way that the location of that first minimum is the same. And so you can totally have weird behaviors like that. And that is something that we're actively looking at. So this is not just a simple crescent. Ironically, we did all that work to understand the biases of the simple crescent because then we wanted to understand what was causing this issue. And then the reaction of other people in collaboration was, oh, you found issues with that one. So then we're just going to use a different one that we don't understand the issues of. And so this is an M-ring model, which is much more complicated, much harder to I think, kind of intuitively give you like a one sentence of what it is. But you're essentially, you have a delta function ring, and then you blur it. And then you add different like modes along that for the brightness. And so you need a full analysis about why that is creating the biases, the correlations that you have. And part of that is included in paper 6, and part of that was done for paper 6, but we're actually working on a follow-up paper that goes more in depth for that, because essentially the calibration was already so much of this paper, and this paper was already like almost 50 pages, and we just ended up having to take all of that out and put it into a different paper, and that will be out hopefully soon. We're working on it, but you know, things take time. Sorry, what?
Time scale of 3 years.
Oh, no, this is not a collaboration paper, so it should not be that. By the summer is what I'm expecting, yeah. Sorry, did you have a question or?
No.
No, okay. Okay. So we, for alpha 2, which is this calibration between the perfect image ring and the ring in the image we actually get, we created a set of synthetic data sets, about 150 of them, and we did a fully blind analysis. And so the idea here is that people in the paper 6 team made this data set and kept everything about it secret, gave it to the imaging and the modeling people. They did all of their analysis, returned the results for us, and then we compared the known values to what they got. And so 150 is way less than the hundreds of thousands that I've been talking about. This is one of the reasons why we separated alpha 1 and alpha 2, because you can totally use hundreds of thousands of images for alpha 1, and that's like numerically and from a person time perspective feasible. But that just was not feasible for alpha 2 because it just took a lot more human time and computational time. And I tried really hard to make that number grow, and this was as far as I could make it grow. And so in these 150 data sets, we include data sets that have the same features as Sgr A, but we also specifically include data sets that don't have those same features. What I mean by that, by features, is features in UV space. So like the data shape looks similar or not. We include both variable and non-variable data sets, and we include various ring sizes and specifically try to find images that have different morphologies as well to make sure that we're not going to be super biased if an image has a slightly different image morphology. And we include both Kerr and non-Kerr images as well. And these are the results of that blind analysis for the imaging algorithms. And so blue diff map, this is like clean, and these other two are RML, like maximum likelihood methods. And so again, fractional diameter difference between the ring in the perfect image and the ring in the observational image. There are, again, slight differences between the different algorithms, which we expected given what we had seen for Sgr A, but they are all broadly consistent with each other, not doing anything super crazy. However, this is what it looks like for the modeling. And so there is a clear systematic error here, and that it does look a little messier. And so we do include it in paper 6, but most of the actual results after the calibration section, everything else is based on the imaging, because there were these weird systematics and kind of some weird behavior going on with the modeling that we just didn't trust it as much. So in addition to alpha 1 and alpha 2, we also have to take into account the previous mass over distance measurement. So there's a lot of work done between people in paper 6 talking to both the UCLA group and the VLTI group, and we were able to get these slightly more broadened peaks that correspond to including what they feel are reasonable systematic uncertainties. And so what we did, as I'm sure everybody knows, there's a very complicated political issue here. And so the way that we handled this is that we, again, treated them like separate but equal. So we did the full analysis for both of these. And in almost every single plot in paper 6, we actually show what the result is for UCLA and for VLTI. And so these are the final bounds that we achieved. So as I've been kind of talking about, there's essentially 24 different combinations of all of these different moving parts, right? So we have 2 different mass over distance measurements. We have 3 different imaging pipelines and also a modeling pipeline. And then we have 3 different alpha 1 calibrations. And so we did combinatorics, and we did the full thing for each combination of these. And that's what each of these lines and these 3 plots are showing you, is how different the final answer is when you use different combinations. And yes, go ahead.
What was the on the x-axis in the previous plot, on the previous slide?
Oh yeah, sorry, theta G, GM over DC squared.
Wait, but I thought it was 50.
No, so 50 is the actual diameter. This theta G is a parameter that we like to use, that we like to constrain, that's effectively the ratio of mass over distance. It is not the size of the ring, but just takes into account the mass measurement and the distance measurement and some constants.
Okay, well maybe
Put into microarcsecond things.
okay.
The point here, this is showing the difference between the results from the UCLA group and the difference between the results from the VLTI, like gravity group. Not just mass difference, but the actual ratio between mass and distance, which is what we actually need for the EHT.
Yeah, I understand that. But so if we, I mean, maybe this is one of the plots that you are going to show, but what's the plot for, okay, let's assume DR is correct and we predict the ring of black compared to theta G, and where does the EHT results, or rather, you know, either convert these to the ring or convert ring to the the angular Schwarzschild.
Yeah, so in this plot, what we do is, assuming GR is correct, assuming that it is Kerr, or actually assuming it's Schwarzschild, this is the range of essentially posteriors that you get. They're not fully posterior, like I'm not really claiming it's a posterior because it's a little more complicated than that, but effectively, these are the bounds that we get on the ring size. If you want an actual, like, what is the mass measurement, we do not do that in paper 6 for a variety of reasons. The main one is that the bounds that we get are so much worse that it really doesn't make sense, right? Because the range that you see in this red shaded region includes both UCLA bounds and Keck bounds, right? So that's in the difference between these two mass and resistant measurement is taken into account.
Right, so they are about 10%, and you're saying that the fractional deviation here is in the ballpark, you know, the width is like, 25% or some, if that's
so
okay. And then for M87, you guys agree with stars, but you disagree with gas, which is not
and the blue shaded region is the Kerr prediction. So the idea here is that we did the full analysis assuming Schwarzschild. So we're always comparing to Schwarzschild. And so if we were to ever have a pink shaded region that's smaller than this blue band, we could actually constrain the Kerr spin, or part of the Kerr parameter space, because it's not just spin, it's inclination as well. But yeah.
And for M87 stars, is that the Gebhardt and Thomas, including dark matter, high mass, 6 times 10 to the 9?
Yeah, I believe so. I can tell you, I can show you the exact paper, but I believe so. Yeah. So this is the actual table that has all of these error bounds for all 24 different combinations. We say about 10%. We're not worried about 10 versus 12 or 8 versus 10. We're saying about 10%, and we're really focusing more on order of magnitude, less so on, the slight differences between them. They are broadly consistent with each other. This is what it actually looks like on the image. So the two solid lines are showing you the range of highest likelihood ring sizes. And again, that range comes from the fact that we have these 24 different combinations, and the dashed curves are showing you the 68th percentile bounds. That includes all of them. And so we use these bounds, and in particular, what we actually ended up doing was using these as the two representative examples. And so all the plots in the following sections after this use those two bounds, but then, refer back to this to see what the effect would be if you had used a different combination. And so obviously 10%, not going to do anything for Kerr. This is showing you the full range of radii for all Kerr as a function of spin and as a function of inclination in the different angles. Absolutely no way that we can do anything for Kerr. But if you take the Kerr metric and you perturb away from it, then you can actually start to do something. So here's just a couple examples of what happens when you use one of these parametrized metrics and simulate what the black hole shadow looks like. So in each of these, this is JP, which is Johansen and Psaltis. The other one is MGBK, which is visual in unison Stein's metric. And in each of these, I'm just varying the one parameter that has the largest effect on the size and seeing what that effect actually is. And so in those two panels, I kept spin constant, but I also want to know what the effective spin is. And so on the bottom panels, I'm showing the radius of the shadow as a function of this like primary perturbation parameter, but then the different colors are also showing the effective spin. And so the point here is that spin still doesn't have that big of an effect, which within Kerr, it kind of makes sense to us why spin doesn't have a big effect because of the symmetries of the Kerr metric. But you're kind of breaking down some of those symmetries here, and you're still seeing a situation where spin really doesn't affect you that much. And so in paper 6, I ran about 24,000 simulations of these different black hole metrics, and these are the constraints. So let me walk you through this because it's a very busy and kind of dense plot. The shaded regions are the regions that we rule out. these two plots here are for JP, and these two are for MGBK. In the top two, the different colors correspond to what happens when I change a secondary perturbation parameter. And the way you should be thinking about this is that this is a hyperdimensional space with a bunch of different parameters, and we have one data point that we're trying to constrain. And so we're going to project this onto different subplanes, right, sort of subspaces of this hyperdimensional space and look at the effects of these different parameters. And so in all of them, the x-axis is the effect of spin. The bottom two, the different colors show the effect of inclination. The point to take away here is not the actual details of all of this, but that we achieve order unity constraints that don't really seem to be that affected by these other different parameters that we're trying to change. And yes, there is a change here. I'm not saying there's no change, but the point here really is order of magnitude. We achieve order unity constraints pretty much independently of which subspace you end up projecting onto your 2D plot here.
Is that something, if things were ordered unity correction, is that something you would have seen elsewhere? I mean, in the sense that are these constraints kind of orthogonal to the constraints from LIGO? I don't know what else would be at
Yeah,
these
very good question.
Distances. Yeah,
We do look into that. I think what makes okay, obviously I'm going to be biased because I worked on this, but I think that our strongest argument is mass scales. So we're probing very different mass scales from what LIGO and Virgo can do. And we are a little independent or a little different from what LIGO and Virgo can do in the sense that we're just probing the metric, we're not sensitive to dynamics, right? And so if you had a situation where the metric was changing, but the dynamics were not, like we could disentangle between those two by looking at both of these results.
somewhat orthogonal, in other words.
Yeah,
yes,
but
and the
also-
mass and the dynamics. Yeah.
Yeah, but they're related enough that at the end I will show a plot comparing the two. Yeah. So you can compare the two.
Maybe you'll get onto
Yeah.
this, but there was a paper, I think it was this morning.
Oh, then I didn't, I was preparing for this and I did not see that. I'm sorry.
That's a good diplomatic answer. Claiming that there's some tension between the spin measurement and what you would expect from the lens steering precession of stars around the supermassive black hole.
What
to the
spin measurement?
The EHT Sgr A star
Okay.
spin measurement. Because if it was, I mean, the claim was, if the spin measurement was as high as is claimed, then you would have lens steering precession. You wouldn't have these kind of disky structures around the FES.
Okay, I will try my best diplomatic answer and then I'll let George give his best diplomatic answer if he would like, but no pressure. We do not claim any spin at all measurements or constraints in paper 6 whatsoever, and I worked hard on making that happen. The way that I personally view the constraints that we have based on the simulations in paper 5, I want to be very clear that I think paper 5 was an incredible amount of effort. Like there is so many simulations that went into that, but you're never going to be able to probe every possible simulation just because that's impossible, right? Like there's always whatever constraints you have, regardless of how broad your simulation set is, like it will still be at least a little bit determined by the simulation set that you use. And in particular, what I think is really exciting is that there does seem to be some new physics that we can learn from this, because the simulations tend to be too variable compared to what the data is actually showing. And so I think that there are two possibilities. One is that the simulations, the results that we have from the simulations are really real, and that we do see a preference for having this black hole have non-zero spin. We don't even really claim a very tight spin bound as far as I know. We just say, hey, this is a set of simulations that we had. These are the ones that didn't have spin and they were ruled out. That doesn't mean that we've explored every possible way that you can make a non-spinning simulation. It just means the ones that we had were ruled out, right? But there's also a really interesting possibility that I personally find really exciting, which is that there might be something that we are missing in the simulations that might actually affect not only this variability, but could also affect other things and might affect these other constraints that we have. George, do you want to comment on that? Because you were more involved with paper 5 than I was.
I loved your diplomatic answer. Let's talk after.
Great.
It's even more diplomatic.
I know, maybe I should have just gone with that. Any other questions? Okay. So these are the plots in paper 6 where we actually use this 10% bound that I've been talking about. And by the way, there are 2 different colors here. Blue is Keck and pink is VLTI. The shaded regions are what we can rule out. Based on the previous plot, what we argue is that, yes, we did this hyperdimensional thing and we tried to vary all kinds of things together. It doesn't seem to vary that much. We just care about this order of magnitude. And because of that, we're going to ignore everything else. And we're just going to assume that these things are not spinning, do an analytic spherical calculation, because I think it's also very nice to actually have like an analytic version where you can actually see what happens in the equations, but that's only feasible if you ignore spin. So anyway, so these are the results from that. So each of these curves in this plot, the curves correspond to these different parametrized metrics where we're ignoring spin and we're just changing one free parameter at a time. And so the x-axis is the value of that free parameter, and when it intersects these shaded regions, that's the bound that we have. The other 2 plots are very similar plot structure, but instead of parametrized metrics, we're looking at specific solutions. So we do include black holes that are not really black holes, they're naked singularities. We include a wormhole. We include the Reisner Nordstrom black hole, and we try to constrain that, right? We include a wide range of black holes. It's not comprehensive. I absolutely am not arguing that it's comprehensive, but we tried to pick some different examples that kind of were representative of the broader spectrum of possibilities. And we do place constraints on a lot of these, and we can completely rule out several of them that are shown over here in the shaded region as well. I'm not going to go into the details of each of these. If you're interested, I'd love to chat, but most people don't care about the details of that. What people might care about, though, is how does this test compare to other tests of gravity? And so from a 2020 paper that I was very involved in, what we showed is that if you write your metric, first you ignore spin, and then you write your metric in aerial coordinates, what you can show is that the photon orbit radius only depends on the time component of the metric. And the radius of the shadow is just the lensed photon orbit, so it follows that it also depends only on the time component of the metric. And so we just need to look at the time component of the metric for all of the analytic work. And what we do is we compare to the parametric post-Newtonian framework. I want to be very clear about this. The way that this is usually done in the testing gravity community is that each subfield has their own kind of pet parametrization that's been specifically developed to work in their subfield that they are playing with, right? And so what we do in our subfield is the parametrized metrics that I was showing you earlier, which are specifically designed for the strong field, specifically designed for black holes. But when the different subfields want to talk to each other, the only way that we can do that is to compare to PPN. And so we do that comparison. And I'm just quoting here the constraints. The point is that we achieve constraints that are kind of less than order unity on the first order corrections to PPN, and we achieve about 5 or so order constraints on the second. And we do this independently for the different parametrized metrics because it does affect it slightly, but you can see that they're broadly consistent with each other. And so we use that to compare to other tests of gravity. So this is just one example of that. Here we're showing what the bounds look like for M87, Sgr A, and the 2 gravitational wave events that give us the best tests of gravity. Gray shaded region is the GR prediction, including the variations due to spin and inclination. And so the point that I want to make here, the reason I like this plot, personally, I think it's actually the best plot we have in this paper. It's my favorite, and I did not make it. But the overall bounds are pretty similar between what we have with Sgr and what we have with the gravitational waves, at least in this one particular parameter, one particular way of comparing them. And we now have strong field constraints on over 10 orders of magnitude, which just a few years ago, we didn't have any of these data points, right? So the field, I mean, 10% error bars are pretty large, but I always say that, you know, we're just little babies learning how to take our first step, but it is still exciting that we're able to put any dots on this plot, right? And so we also showed this plot in the paper, and the point here is, again, we're trying to compare, but now not just compare it to gravitational waves, but compare it to like the broader landscape of tests of gravity. And the way that we like to do this, and this, by the way, this plot was not invented for paper 6. This has been around for a long time. I think the first time it was published was by Tessa Baker. I want to say 2010, but don't quote me on that. Oh, 12? Regardless, if you want, I can share the paper with you.
Saltis was showing this.
Yeah, because he's a co-author on Tessa's
So
paper.
I think this is much older than that.
Yeah. Yeah. And so what we're comparing here is curvature versus gravitational potential. So a simple way to think about this, right, is that M87, Sgr A, and the gravitational wave experiments, they're all probing the strong field very close to the black hole. And we're actually probing very similar distances from the event horizon, actually. So we're probing very similar gravitational potentials. But because we're probing such vastly different masses, we are probing very different curvature potential or curvature ranges. And so, you know, this is kind of the parameter space that we like to think about for tests of gravity. And so it is kind of fun to put another dot on the plot in a different location. And so I think I still have not a lot of time. Okay, I want to get through this because I think it's a really cool part of what we did, but I'm going to try to get through it quickly. So in addition to everything else, we also just explored the question of, does this thing have an event horizon? Right, like can we, obviously we all expect it to have an event horizon, but can we actually use these results to constrain that? And the way that we wanted to approach this, honestly, is a very astrophysical way of approaching this, and I totally own that. But we essentially identified three possibilities, three alternatives that we wanted to constrain. One is that there is a surface that absorbs incident radiation, gets heated up, and re-emits it thermally. Second, it could be a reflective surface. Or third, it could be a naked singularity. And so naked singularities, we can rule some of them out and others we cannot. And so I cannot say conclusively that we can rule out all naked singularities because there is a pretty wide range of naked singularities in the literature and we did not go through every single one. And I know that there's some.
Astrophysically, I mean, you gave an astrophysical one-liner for reflective surface thermal.
Yeah, well, I was going to go into a little bit more detail, but the naked singularity ones are really weird because we don't really have a self-consistent like physical description for them. So yes, tons of assumptions go into that.
Okay.
Yeah, a ton of assumptions that you might feel very uncomfortable with. We're pretty uncomfortable with them too, but we're just doing the best that we can to try to understand what would happen, right? And so essentially you just put a boundary condition very, very close to the singularity and you're like, okay, well, if it got this close to singularity, I'm assuming that it's now part of the singularity and it has left my simulation domain.
How is it different from the horizon?
The radius of the boundary is different. Yeah, that's pretty much it. Sorry, but it's not a very.
But it's basically a horizon just at the wrong distance from at the wrong distance.
Well, yes, but the fundamentally the metric is different as well. Right. So it is a singularity metric. Computationally, we still do put in a boundary condition at some point.
Okay.
Yeah.
So it's a combination of horizon being the wrong distance and the metric being somewhat different.
Yes. Yeah. But this plot is actually about the thermal surface. And so this model has been around for a while. I think the first papers were by Ramesh Narayan and Avery Broderick, and I actually asked Ramesh to lead this section because of that. And so this model's been around. There have been constraints on it. There's a couple different knobs that you can turn. And it turns out that the most powerful knob that you can turn is the size of the emission region. And that's what we can constrain with the EHT. That's like the new piece of information that the EHT has contributed to this conversation. And so it's using that size, like the scale of the emission region that the EHT has constrained in our images, and using reasonable estimates for the accretion rate. And by the way, these solid curves are showing you the range of reasonable accretion rates that we expect. This is the flux that you should see at infrared wavelengths, and this is the actual measurements. And so we can essentially rule this out pretty much completely, which is pretty fun because this has been around in the literature for a while, and there was always a little bit of wiggle room because we didn't know how big the actual emission surface would be, but this has conclusively killed it. And the second thing was this reflective surface. And so the top row here, this is just a regular GRMHD with a normal event horizon. This is a perfectly reflective surface, and the bottom two, this one's albedo 0.3 and this one's albedo 0.1. The middle column is when you blur it, and the rightmost column is when you actually do a synthetic simulated observation fully. And so what we say is that we can rule out albedo of 1. Albedo of 0.3 I think is highly unlikely given our results, but I'm not comfortable fully claiming that we've completely ruled out a reflective surface. We've just ruled out a perfectly reflective surface. But also what Ramesh keeps wanting me to point out to everybody is that this is a proof of concept. It is not nearly as robust as the other model because all of this ignored spin. And so there are projects that people are working on now to kind of take this several steps further, including spin, including, you know, variability and all of that, because it's also just the average image that we're comparing. And so I'm out of time, so I'm going to skip all of this. But this is an advertisement for a paper coming out about how this will be better in the future. So you can ask me about this paper. Look, the image could look like this instead of this. Yay. Okay. Sorry, all these builds make it a lot harder. Okay, so I'm just going to go through my summary quickly and then we can take questions. And I am sorry, I feel like I went way over, but also I feel like we had good questions. So hopefully people aren't too upset. So the first image of Sgr A is completely consistent with the predictions of a Kerr black hole. I feel like whenever I talk about this, I don't really emphasize that enough. So now I've made a point at actually putting this in all of my summaries. Like, yes, we don't measure any deviations. Nobody's really that surprised. We use hundreds of thousands of Kerr and non-Kerr simulations to calibrate our uncertainty. We arrive at about a 10% uncertainty between the diameter of the black hole shadow and this observational ring. And we use this 10% uncertainty to constrain deviations from Kerr, both parametrically and with specific known solutions, specific other metrics. And we also constrain alternatives to an event horizon. And I'll take questions. Thank you. Yes.
Yeah, I want to ask about the 10%. So the KEC and VLTI by themselves have a 10% difference in mass, or in the theta G. Is that correct? That was the main reason why you have a 10%.
Sorry, I should just click. Hold on. This is gonna take too long. Let me go back to it. Okay. So it's about a little
Not really 10%.
a little higher than 4.9 to about 5.1. Significantly smaller than 10%.
So
And
so the 10% actually comes from your the emission range has a finite size, right? And
so this
the-
10% includes this uncertainty. It includes the alpha-1 calibration and it includes the alpha-2 calibration. That's
The
all put
position and the width of the ring.
well, no, it includes the uncertainty between the analytic feature and this perfect image, and then it includes the uncertainty between the perfect image and the observation.
Yeah.
Yeah. And so the 10% mostly comes from both this theoretical uncertainty and the observational uncertainty, but this is included in that as well.
Yeah, I totally understand it's all included, but it's dominated by the emission. The emission itself, it's a thick ring by itself. It's not, so that you can't really, it's not a thin, absolutely thin ring. So is that what's dominating the 10% at this point? Meaning that even if you improve in imaging resolution, you won't beat that 10%.
Okay, so I think I understand what you're trying to get at, but let me try to put it into the context of what we're talking about here. Alpha-1 is what I consider the theoretical uncertainty, and that is a significant uncertainty, and we won't really get past that in the future. I mean, we might, but I mean, like not in the next couple of years, probably. If we had a situation where we were seeing a really, really thin ring when we get higher resolution, better modeling, whatever, then we would use the argument that, well, the ring is thinner, and so it has to be contained within this bound, and so then the error bar would go lower, and so the theoretical uncertainty would be lower, right? And that's one way that the theoretical uncertainty would be lower. The second part is alpha-2, which is the fact that we don't have enough telescopes, really. And so we observed in 2018, 2021, and 2022, and in all of those years, we had additional telescopes. I think that alpha-2 will go down. Yeah. Which one dominates? I think they're actually pretty similar.
Yeah,
but
because if you take 5%, 5%, 5%, square them and add them in quadrature, you get just about 10%. So
yeah,
sounds like
yeah. And all these numbers, I mean, I don't have all of them memorized off the top of my head, but they are all quoted. And so if you actually do want to know what alpha-1 actually is, like I can tell you in like 10 minutes.
Yeah, I have one more question on the thermal surface. So if I have a structural case, non-spinning case, my thermal surface is just above the horizon by a tiny bit, by let's say the Planck scale. It's not going to emit anything, right? Because it's so redshifted, right? How was you're saying you have completely ruled out the thermal surface?
Yeah, within certain assumptions. Yeah.
Well,
And so one of the assumptions is that the light does actually leave. Right. I mean, if you're at the Planck scale, yeah, that's not included.
Not necessarily the Planck scale, let's say 10 to minus 10 fractional deviation, but above the structural radius, right? I was thermally emitting surface at the m dot. M dot.
Yeah, so the way that you should
So
think about
redshifted,
this.
it won't emit by the, at infinity, you won't see that surface emission.
I believe that the redshift is included here. It is included in the model,
Is it
but I do think that a pretty strong assumption is that I think the total energy does get out eventually. I think we do assume that the light does actually escape, but it can be redshifted. That's fine. It can have all these different effects on it. That's fine, but we do assume that it does actually escape.
But they may not escape, right?
Yeah,
Because
and that's not included in the model. Yeah.
Let's say imagine a tiny patch in a local patch on that surface. It has an I nu, that's intensity, which is isotropic, like the photosphere of the sun, but only a tiny solid angle, nearly exactly perpendicular to that surface can get out. Of course, there is a single beam which is exactly perpendicular. That will definitely get out, right? But there's a tiny solid angle. All the rest of it will bounce back to that surface.
So I totally get what you're saying, and I do think that is a very real limitation. We are treating this very much astrophysically with the understanding that there are ways that you could create surfaces that are really close to the event horizon that would be indistinguishable. Like fuzzy black holes, for example, like we did a whole thing on that. And yeah, you can't tell.
Not that I believe any of
you can do all kinds of weird quantum mechanics things, or you can play with like the Planck scale and you can totally create surfaces. Yeah. I'm not arguing that it's impossible to have. I'm not claiming that we've proven that it's an event horizon, right? It could still be a naked singularity, and there are other weird surfaces that you could have. But in this particular model that's existed in the literature for quite some time, we were able to rule this model out.
So basically, you're saying, from the observer's point of view, you're seeing the m dot c squared coming out, right? That's the underlying assumption on some of those curves, right? I see.
Yeah, and also like if you're interested, we can go through the map. Like it's fairly simple, like I can show you what the assumptions are in more detail later. Yeah.
So without using the prior measurements, you could produce this kind of plot for just from your data. What is the probability of theta g? It would be, I guess, broad, but
yeah, it would be huge. Yeah. That is in one of the other papers.
I don't have that.
Yes, I argued really strongly that I didn't think we should do that. I don't think we should.
Like just because broad at the moment compared to this.
Yeah, because I don't think it's adding anything, honestly. I don't think it's new information, and I think it's just a little ridiculous compared to the other constraints we have. And I feel like what we can do is, assuming these constraints, we can actually test something new and exciting, or we can just say, yes, we measured the mass that's consistent with what we knew, but with huge error bars, which, I mean, it's not as exciting to me.
But in principle, you may be able to approach this uncertainty, not just independently from your own.
We
in a
don't.
few years.
Maybe, yeah, but we're nowhere near. Any other questions?
Can I ask this spectra that you showed here, one of the last slides?
The thermal thing?
I think where is the spectra, recent models, comparisons with data.
Yes,
this one.
Yes.
So these data points are below all of these curves. Does it mean that accretion rate is just very low? What is
No. So this is the thermal surface model.
Oh, okay.
Yeah, and so for the accretion rate that we think is reasonable, that we expect on all kinds of things, this is what you would have if you had a thermal surface. Yeah, and so we're not claiming any issue with the accretion rate. We're just saying that given the assumptions of this model, we can rule out this thermal surface. Yeah.
Oh, I see. Do we have other questions? And also people online? No? Well, yeah, I think we have a perfect end for the seminars this semester. So thanks, Lia, and thank everyone here.